Chemistry 3101, Chapter 9. This is where we left off in the last lectures that we were talking about the hydration of an alkene. And if you remember, or an alkyne, excuse me, hydration of an alkyne. And the reason I was thinking about alkenes is because you remember in the alkenes chapter, we talked about reactions like this one. I'll just give you an example reaction where we have an alkene like this. And we said, well, if we want to do a Markovnikov addition of water on this alkene, and avoid carbocation rearrangements. First, we treated it with mercuric acetate and water, and then in the second step, we did a reduction with sodium borohydride. So this is called oxymercuration, demercuration. Again, this is a question, or a reaction rather, from the alkenes chapter. So alkenes, put that there, alkenes. But now we're going to talk about the hydration of an alkyne. And the hydration of an alkyne will not work by simply treating the alkyne with aqueous acid. We saw that we could do that with an alkene. However, we would use mercuric acetate when we wanted to avoid a carbocation rearrangement. Well, there's no carbocation rearrangements that we're going to worry about with respect to alkynes. However, we need to add a special reagent in order to get this reaction to go forward. And that reagent is HgSO4, which is mercury 2 sulfate or mercuric sulfate. So what do you have to remember? You have to remember that you're going to need a source of acid and water, sulfuric acid and water, but you need this mercuric sulfate. And the reason why is because without it, the reaction is just too slow. Okay, and it's because of the formation of a vinylic carbocation. Now, again, where we left off last lecture was talking about an enol. And when you do the Markovnikov addition of water across that triple bond, look, you've got a hydrogen here, and you have no hydrogen on this carbon that I just highlighted in blue. So the hydroxyl is going to go on that carbon, and the other hydrogen is going to go on this carbon right here. So we end up with this new functional group, which is called an enol, and you can guess where that comes from. It comes from alkene, right here, and then the alcohol, right, which is right there. So we have an enol. Well, an enol is actually not stable the way it's written, and that's why we have these little square brackets written around it. We could put here unstable. Okay, there are some conditions under which an enol will be stable, but that's not going to be of any consequence to us in Chapter 9. So the enol is going to undergo a rearrangement, and that rearrangement has its sassy word. It's called tautomerization. So tautomerization, which is nothing more than a type of isomerization that involves the migration of a pi bond and a hydrogen atom. So the tautomerization that occurs here is going to occur in acid, so in H+. And the reason why is because we're using sulfuric acid and water. So you don't have to know the mechanism for the formation of the enol. However, you do have to know the mechanism for tautomerization. So let's take a look at that mechanism. Good news is it's a very short mechanism. First is just a proton transfer. So our double bond, the pi bond, behaves as a base and it takes on a proton. Then we get a resonance stabilized intermediate that's right here. So first we form the carbocation, then a lone pair comes down from the oxygen to stabilize that carbocation so that every atom gets a complete octet, right? Here this carbon doesn't have a complete octet, but here everything does have a complete octet. And then water is going to come in and affect a second proton transfer to produce a ketone. Now, some more terminology here. We say that the enol and the ketone are tautomers of one another. So the process, again, is tautomerization to go from here to here, and the enol and the ketone are tautomers. So you'll hear me say tautomers from time to time. And again, this is a mechanism that you must know, okay? So know the mechanism. This will come up several times in organic chemistry. But the good news is it's just two proton transfers followed by a quick resonance structure that you have to draw. So a resonance stabilized intermediate. Anyhow, let's move on from there and talk about how would we hydrate an internal alkyne, right? If you go back here, we were talking about hydrating a terminal alkyne. Remember that when we have a hydrogen on the end like this is called a terminal alkyne. Well, an internal alkyne means that the triple bond is going to be flanked by two R groups. So this is an internal alkyne when we have two R groups on each end of that triple bond. So what would happen then? Well, if we do the same reaction, treat the alkyne with sulfuric acid, water, and mercuric sulfate. Remember, we need that to motivate the reaction to get it to go. You'd actually end up with a mixture of ketones in this case. And I mean a mixture if the R1 and the R2 are different. Okay, if they're identical, then you don't end up with a mixture of ketones. But generally speaking, we're thinking about different R groups. So R1 and R2 are different, and you see you end up with two isomers, right? You end up with two different compounds here. So this reaction is I don't like to say less useful because every reaction in organic chemistry has its place and its time. But I would say this reaction is maybe a little less synthetically useful since mixtures are something that we like to avoid in organic chemistry. Anyhow, let's take a look at a question. This would be a perfectly reasonable question for an exam. It says, draw the major products expected when the following alkyne is treated with aqueous acid in the presence of mercuric sulfate. So what does that mean? We're taking it and we're treating it with sulfuric acid and water, and we're going to use mercuric sulfate to get that reaction to go. Well, remember, this is a terminal alkyne. The rich are going to get richer. So the carbon that has the red proton attached to it, that's the one that's going to take the proton from the water. This carbon over here is going to take the hydroxyl. What are we going to end up making? We're going to end up making an enol, aren't we? And the enol will look something like this. So it's going to look something like this. Then we get this tert-butyl group down here. But we know that an enol is not going to be stable, right? The enol is going to undergo tautomerization. So I'm just going to write TAUT to abbreviate tautomerization. It's going to undergo that tautomerization of the enol to give us a ketone like this. And you probably notice that it's not just any kind of ketone, that they're methyl ketones, right? This group here is always a CH3. That's a methyl group, right? If we go back here, right, this is a methyl ketone when we treat a terminal alkyne with sulfuric acid, water, and mercuric sulfate, right? Same thing here, we get a methyl ketone. All right, so now we're going to do the same type of exercise, but we're going to go backwards, right? We're going to start with a product. And let's say somebody comes up to you and says, you know what, if you can make this product, you know, and make enough of it that we can sell it, I'll give you, you know, $2 million. Like, I could use that. You know, that's a little bit, you know, that's some good money. I could use that. So what are some ways that you could do this? Now, if you're very astute and you know, well, that's a methyl ketone right here. This is a CH3 group. You know, you might be fast enough to just say, well, all I would have, excuse me, would be this alkyne, right? If I had that alkyne and I simply treated it with sulfuric acid, water, and mercuric sulfate, right? That's going to give me an enol, which will produce the desired ketone. And there's nothing wrong with that. Okay, that would be a perfectly legitimate approach to solving the problem. However, if you're struggling with that right now, if you're like, I'm not sure that I could get committed behind, you know, making a decision that quickly, what you could do is you could say, why don't I draw the enol, right? Why don't I draw the enol intermediate? And if we draw the enol, it's going to look something like this. So instead of a double bond to our oxygen, we're going to have a single bond to our oxygen. And instead of a single bond down to the methyl, we've got a double bond here to a methylene, to a CH2. Now, if you have this enol, it might help you to go backwards again, right? This is a retrosynthesis arrow, and say, well, these two carbons right here in the enol, those are the ones that are going to be in the triple bond, like that. So then you kind of cobble it all together and you say, well, if I had this starting alkyne and I treated it with mercuric sulfate, sulfuric acid, and water, I'd end up producing the enol, which will undergo a tautomerization to produce the ketone. Give me a thumbs up if that makes some sense to you. If you're thinking, you know, I think I could do that. Cha or no? Okay, good. Thanks, Moira. Great. All right. So again, we're just doing what's called retrosynthesis. We're thinking backwards. Okay. All right, let's try the next one. We have another ketone here. So this is 1, 2, 3, 4, 5, 6. So this would be 3-hexanone. That's neither here nor there. We're going to talk about ketone nomenclature in chemistry 3111. However, the same rationale here. If we were to think backwards, right, if you're not sure where to go, why don't you just say, I'll make an enol right here. Okay, so I'll draw the carbon skeleton out like this. I'll put a double bond here and I'll put a hydroxyl here. Well, if I had that enol, it's going to undergo tautomerization to give me the desired product. And so what would be the starting material that I would need? I would need 1, 2, 3, and then I need a triple bond. I have to be careful about my geometry like that. Okay, so that would be the starting material. And of course, I'm going to treat that with sulfuric acid, right? You write these conditions down enough times and you'll remember them. And mercuric sulfate, like that. Now, that is the correct answer. Okay, I'll give that a big check mark. Okay, there's nothing wrong with that answer. You might have said, well, hold on, Mr. Dion. What if I had made the enol here? You know, would that be is that a possibility? You know, if you said, okay, I'll just make my enol right here like that. Okay, and that enol will undergo tautomerization to give me the desired ketone. There is a problem with this strategy. Okay, let me show you what it is. If we go back another step and we draw out the alkene that we would start with, we have 1, 2, 3, 4, 5, 6. And think about it. If you were to take this alkyne and if you were to treat this with sulfuric acid, water, and mercuric sulfate, okay, you're not going to get just that enol, will you? Because you see that the R1 group and the R2 groups, they're different. So you'd actually end up with a mixture in this case, okay? Not only would you get the compound that's highlighted in green, but when you treat it with that mercuric sulfate, sulfuric acid, and water, you would also get, and I'll write the product down in yellow, you would also end up getting this ketone. So 1, 2, 3, 4, 5, 6. You'd also end up with this guy, okay? Same thing. All right, so you'd end up with a mixture of this ketone and the desired product. Mixtures are not good. If you use this starting alkyne, you only end up with this product, only one product. Give me a thumbs up if you follow me on that concept, or stop me if you have a question about that. But we prefer to avoid mixtures when we can. Organic chemists don't like getting mixtures because you guys have all, well, I haven't really set up any reactions in chemistry 3102, but I can tell you from personal experience that setting up a reaction isn't that difficult. You know, all these reactions that we write down, you know, borane and all this mercuric sulfate, you know, setting up a reaction is not that difficult. Where organic chemistry gets difficult, in my opinion, is when you have mixtures and you have to separate them. Separating compounds actually chews up just as much time in an organic chemist's life as setting up reactions and designing new reactions and things like that. All right, well, let's move on and let's talk about the anti-Markovnikov addition of water across an alkyne. Good news. You remember hydroboration oxidation of an alkene? Well, we're going to use a similar, not identical, but a similar approach to doing an anti-Markovnikov addition of water across a triple bond. So let's see here. It says hydroboration oxidation of an alkyne is the same as that for an alkene. It's regioselective, and that we get anti-Markovnikov addition. You probably notice right away that we end up with an enol. Again, but when this enol undergoes tautomerization, we don't get a ketone, we get an aldehyde. Okay, we end up with an aldehyde. So you take a terminal alkyne, you treat it with borane, THF in the first step, hydrogen peroxide and sodium hydroxide in the second step, and you get an enol that tautomerizes to give you an aldehyde. Well, hold the phone. Now you're in base, right? You're not in acid anymore. You're in hydroxide. And so the tautomerization occurs in base. And so this is going to be a little bit different mechanism. And you need to know the mechanism of base catalyzed tautomerization. So you need to know this mechanism thoroughly. What do? You take that enol, the base is going to deprotonate it to make what's called an enolate, right? Whenever you see 8 in chemistry, 8 is, think of negative charge, carbonate, sulfate, nitrate, etc. So we have an enolate, right? We have the enol, and it's got a negative charge on it. So we have an enolate ion, which undergoes a resonance stabilization. Okay, so we have the second resonance. It's not a stabilization, I shouldn't have said that, but it has the second resonance structure here where we can draw the negative charge on the carbon. Then we have a proton transfer from the water that was formed in this step. So this is the water molecule over here. And there you go. You produce your aldehyde. So how many, steps is this? It's 2 proton transfers followed by a resonance, 2 resonance arrows here for the enolate ion. So you have to know this mechanism. Now, like many things in organic chemistry, there are some pitfalls with reactions like this. And let me show you what the pitfall is here. you are never going to use these exact same conditions to do the hydroboration oxidation of an alkyne. We will never use those exact same conditions. Let me tell you why. The reason why is because an alkyne is composed of a sigma bond and two pi bonds, right? And we know that a double bond, a pi bond, can react with borine. This is the BH3 molecule here. And we discussed this when we looked at the mechanism of hydroboration oxidation in the alkenes chapter. But hold on, after the first addition of borane, you form this intermediate here, but you've still got another double bond, which can react with a second molecule of borane, and then you end up getting undesired products. Now, the book doesn't go into any more detail than that, but I'll just tell you that after the first addition, okay, you don't want this to happen. You want to avoid that. And you're wondering, how do I avoid that? Well, it's actually not that difficult. The way that you avoid that is instead of using BH3, we're not going to use BH3. We're going to use what's called a dialkyl borane. And there are a few different dialkyl boranes out there on the market. Now, I've taught the class long enough to know that the preferred dialkyl borane of my students is 9-BBN. So it's got this big name. I'm never going to ask you how to name a bicyclic compound that has boron in the structure, but it's 9-borobicyclo-331 nonane. That's neither here nor there. Another option for a dialkyl borane is this molecule here. It's called Dicyama Borine. And what these two reagents have in common is that they have big, bulky alkyl groups attached to the boron, right? Here's your boron, here's an alkyl, here's an alkyl. Here's your boron, and it's got all this alkyl group attached to it, right? So it's got this big, bulky alkyl group. What does that do? It prevents this from occurring, right? By the time the first addition has happened, it's so sterically hindered, your alkyl boron, that this part is not going to happen. So that is why we have to use a dialkyl borane. Now, a couple more things about the dialkyl borane. Again, I've taught this class quite a while, and my students love the David Klein Solutions Manual with good reason. It's very well written. I believe that in the Solutions Manual, he probably uses 9-BBN most of the time because my students always kind of get obsessed with that reagent. And you know what? There's nothing wrong with that, okay? There's nothing wrong as long as you understand what 9-BBN is for. It's a hindered borane, and so it's going to prevent that second addition. It's going to prevent undesired products from occurring. There are two more nuances to this, though. If you're the kind of person that likes to peruse the internet, you know, if you were like go home on a weekend and say, I can't sleep, I need to Google hydroboration oxidation of an alkyne. Besides Dicyama Borine and 9-BBN, here are some things you might see. Instead of writing out the alkyl groups, sometimes you'll just see people say R2BH like this, right? And the R2 means the big or the bulky alkyl group, okay? Another option, and this is something that you'll see in the ACS study guide, if any of you have the ACS study guide, is sometimes they will write this. They'll put the boron attached to a hydrogen, and then they put it in a kind of a funny looking thing like this. And what this means, this like goofy looking thing here, like what is that? I've never seen that. That means it's a bicyclic structure, so bicyclo. So that means it's just a big bulky bicyclo, is all that means. And again, this doesn't come up in our textbook at all. It does come up in the ACS study guide, I think. And then this might come up in the ACS study guide as well, or other textbooks. You know, I have students who might, again, be perusing the internet and looking at other textbooks, and there's nothing wrong with that. Nothing wrong with that at all. Okay, so there we go. So overall, what did we learn? We learned that if we take a terminal alkyne, we treat it with a hindered borane. And again, it could be Dicyama Borine. It could be OR 9-BBN, which again, I told you my students seem to have really enjoyed. Or it could be just R2BH, that works. And that bicyclic thing, I'm not going to draw that right now. It could be any of those in the first step, just a bulky borane, followed by hydrogen peroxide and sodium hydroxide, and you end up producing an aldehyde. Pretty cool stuff, huh? Okay, very cool stuff. Well, if we summarize what we've learned in section 9.7, it's this. If we have a terminal alkyne, and we take that terminal alkyne and we treat it with sulfuric acid and water and mercuric sulfate, we do a Markovnikov addition of water, which forms an enol. Now, the enol isn't drawn on here. I just can't help myself but to draw the enol just for fun. And then the enol undergoes a tautomerization to give you a ketone. I'll just leave it here in the square brackets, okay? Also, if you take a terminal alkyne, you treat it with a hindered borane, and the first step could be 9-BBN. Look, I even wrote R2BH here, so son of a gun. There you go. All right, what do? You end up producing an enol, but now the enol looks a little different, doesn't it? Right? You end up with an enol that's going to look like this, okay? Because you're doing the anti-Markovnikov addition of water. So the carbon that has the hydrogen, this is the one that's going to end up with the hydroxyl on it, okay? So we end up with a different enol, which is simply an isomer of the one above it, but that's going to tautomerize to give you an aldehyde. And that is a summary of really what you learn in section 9.7. With that under our hat, let's see if we can try a practice problem that says identify the reagents that you would use to achieve each of the following transformations. So instead of me just asking you what the reagents are, if I wanted to take this terminal alkyne and I want to convert it to a methyl ketone, would this be a Markovnikov addition of water or an anti-Markovnikov addition of water across that triple bond? Just mark or anti-mark, what would it be? Yeah, exactly. All my students are nailing it, right? It's a Markovnikov addition, isn't it? If it's a Markovnikov addition of water, what are we going to use? We're going to use sulfuric acid in water and mercuric sulfate, or mercury 2 sulfate. Okay, next one, we're going to take the terminal alkyne, right? Both of these are terminal alkynes, and we want to make an aldehyde. Well, this is going to be an anti-Markovnikov addition. Now, we can't just use BH3 and THF, can we? We have to use a hindered borane. Let's get spicy here. Let's just use 9-BBN just because it's such a cool acronym. And then for the second step, we're going to use hydrogen peroxide and sodium hydroxide, right? And of course, both of these reactions, remember that both of these reaction conditions first produce an enol, which undergoes tautomerization to give us the ketone and the aldehyde respectively. But that in a nutshell is what you need to know about section 9.7. Markovnikov addition across a triple bond, terminal triple bond, to give you a methyl ketone, which we're going to use a lot, and then anti-Markovnikov addition across a terminal alkyne to give you an aldehyde. And you can imagine where we're going with this, right? In organic chemistry 2, we do a whole chapter where we look at the chemistry of ketones and aldehydes, and we learn a crap load, pardon my language, of new reactions where we can use aldehydes and ketones as starting material. So there you go. All right, well, let's move on to section 9.8 to something that's near and dear to your heart already, which is halogenation. You guys remember the halogenation of an alkene where it proceeded through the bromonium ion? Remember the cyclic bromonium ion, and then you get the anti-addition? Well, that was in the alkenes chapter. With alkynes, you're going to see that there are some differences. Halogenation of an alkyne, if you just take just a regular old run-of-the-mill alkyne and you treat it with a bunch of halide, so it can be either Cl2 or Br2, right, which is what's being said here. You can't use fluorine because that's too fast, okay, it's too violent, and it can't be iodine because that's too slow. But if you treat the alkyne with excess chlorine or bromine, you make a tetrahalide. Look, you got 1, 2, 3, 4, right? And it seems like it proceeds in a decent yield. Okay, well, that's making a tetrahalide. Now, what if you only used one equivalent? Now, this is where it gets kind of interesting, and we're going to talk about a mechanism that's not even completely understood. If you take the alkyne and you treat it with one equivalent of X2, okay? And then, again, X2 can either be bromine or chlorine. It's not going to be fluorine. It's not going to be iodine. What you end up with is 1,2 addition across that triple bond to make a dihalide, but you end up with a mixture, okay? Because you get both anti and syn addition. So you end up with the trans compound and the cis compound. Now, hold on. If you're like, well, what you taught me in the alkenes chapter was that it's going to be an anti-addition because of the bromonium line. Well, since we end up with a mixture in this case, that gives us a clue that the mechanism is actually not really understood for this reaction, okay? If it was to proceed through a bromonium, like it did for the alkene, that means that you'd only end up with the trans product, right? You'd only get anti-addition, but we don't. And so sometimes we kind of have to throw up our hands a little bit in science, right? And say, well, you know what? We don't understand everything, do we? No, we don't understand every single thing. If you are the kind of person who enjoys social media, you might think that, you know, the scientific community knows everything about everything, but we certainly don't, right? anyhow, you think about, I was born in, in the 70s, and think, would any of you want to go back to living in 1980, let's say, and live with the medical technology that we had then? It's only 41 years ago. It's not that long ago. And I guarantee you that most people would say, no, I don't want to go back to that, right? So we have made advances. And so we didn't know everything then. And I think 40 years from now, we're going to be able to say the same thing. All right. Anyhow, let's move on from there and talk about a new reaction. So I'm kind of blasting a reaction at you with the halogenation. We just went over that one quickly. Again, no mechanism for that one. But let's take a look at ozonolysis of an alkyne. Now I'm just going to pencil this in down here, and I'll probably scribble it in the end. But I just want to refresh your memory. You guys remember this chestnut from the alkenes chapter, where you took a alkene and you could treat that with ozone in the first step, and then in the second step you treat it with DMS. Remember that? And you could bust out the eraser, and well, that didn't work, did it? But anyhow, you could break out the eraser, and it would show you how you'd end up with, two equivalents of an aldehyde. So you'd end up with that. That was the alkenes chapter, right? So I'm gonna erase that. That was just a refresher for your memory. So the first step was ozone. The second step was DMS. Now I'm gonna delete. There we go. When we're doing the ozonolysis of an internal alkyne or a terminal alkyne, the second step is not DMS. It's not zinc, okay, because sometimes we use zinc and water. Anyhow, if we do the ozonolysis of an alkyne, the first step is ozone, second step is water, okay? So we could even write that down here. The ozonolysis of an alkyne, first step is ozone, okay? Second step is just good old throw some water on it, okay? Now what's going to happen? You can still kind of try that same pencil trick or the eraser trick where you scribble this open here, and then what happens is you end up with the carbon forming a double bond to one oxygen and then a single bond to the other, and it produces a carboxylic acid. So when you do the ozonolysis of an internal alkyne, you end up with two carboxylic acids. If you have excuse me, a terminal alkyne, you end up with one carboxylic acid from the R group, and then the other one just produces carbon dioxide gas. So that just would bubble out of the reaction mixture, right? CO2 is just a gas. Okay, so there's another new reaction for you, and our book doesn't go into any detail on the mechanism of this. Zero. So if it doesn't go into any detail, you can imagine that you don't have to produce any details on that. So again, predict the products of the following reaction. We have this symmetrical alkyne. You see that both sides are the exact same. Look, if you want to try to do that eraser trick, and I've never done this before, I swear on the Bible, okay, but you could try and do it kind of in a goofy way, I guess. There's probably a reason it's not in the book, right? So we could scribble this, and then you say, okay, and on one of them I'm going to get an oxygen, and on the other one I get an OH, right? And here again. Okay, that is ridiculous. But anyhow, the idea is that you end up with your cyclopentane here. You have one carbon, and then you're going to have your carboxyl group, and you're going to have that happen twice. Okay, now before we move on, and you just say, yeah, that's easy, I can do that, no problem. I'm going to leave this on here just for giggles. Before you get into saying, oh yeah, this is easy, just carboxylic acid, no problem. What I've seen students do in the past, and don't write this down and don't do this, okay? Do not scribble this down if you're making notes. I've seen students do this, so they'll say, yep, here we go. There's my carboxylic acid, get two carbons here. There you go, two carbons. Whoa. That's wrong. That's adding an extra carbon, okay? You're going to cut right here. So that means you have a carbon here in the ring, right? The next carbon is the one that's got the carboxyl group on it. Don't start saying, well, I got two carbons, so that, must be here. No. That would be very, very incorrect, okay? So that's just a trap. It's not a trap, but it's a mistake I've seen students make along the way. And whenever I catch those kind of things, or I see them happen more than once, I try to warn you guys about it, red alert. Anyhow, there you go. So summary of that is you do the ozonolysis in the first step. The way that you produce ozone is you don't have to go up to the atmosphere and, grab it and put it in a trash bag and bring it back home. No, ozone is actually made in the lab using an instrument or a machine called an ozonizer. I'm not going to go into the details of that. Suffice to say that ozonizers are kind of loud. Has anybody here ever used an ozonizer at home before? I think I asked a class this one time and got like no response. People just said, well, "Are you crazy?" Has anybody ever heard of using an ozonizer in their house before? It's not uncommon. You can rent them for not a lot. Ozone is toxic, so you don't want to be in your house. I've used ozonated water. Okay, well, an ozonizer. I'm glad that none of you have actually rented an ozonizer, because usually people that are somebody who maybe smokes in their house, you know, if somebody smokes a lot in their home, and I mean smoking cigarettes, um, the ozonizer can be used to remove odors. Also, you know, if you have a horrible odor in your car or something, if somebody spilled something like maybe milk or, you know, I don't know, but an ozonizer. Another example that I could think of an ozonizer would be just if there was a fire. You know, if there was a small fire inside a house and it got repaired and then you could still smell the smoky odor that's left over, you can rent an ozonizer. You could Google it right now and just say like buy ozonizer, and it don't cost that much. But they make an annoying sound, like kind of a sound. Anyhow, I'm not going to quiz you on that. Okay, not going to quiz you on that. One more thought about this whole idea of a symmetrical alkyne like this one here. It's a pretty cool reaction if you could take advantage of it, because if you start with 1 mole of starting material, you end up with 2 moles of product. Now that, my friends, is a pretty cool reaction, okay? Usually in organic chemistry, you end up with less than we started with. But if you can, you know, double the quantity or double the number of moles, not that you're not going to double your mass, but if you double the number of moles, it's pretty cool. You know, years ago I went to a conference and a guy stood up and he said, you know, the best kind of organic chemistry to do would be theoretically if you could just dump all the reagents, you know, all your starting materials in a bathtub, stir them around with a canoe paddle, and then pull the plug out of the bathtub and collect everything in the bottom with a Home Depot bucket, you know, and just collect a white crystalline solid. He said that would be ideal, but unfortunately, organic chemistry doesn't work that way. Anyhow, I digress. Let's take a look at a problem. So this is question 9.24, comes straight out of your textbook. It says, draw the major products that are expected when the following alkyne is treated with ozone followed by water. Well, we're going to take this guy and we're going to treat it with ozone in the first step. Ozone is a gas. Second step, we're going to treat it with H2O, throw water on it. What are we going to do? We're going to cut right here. So here's an exercise in counting carbons. Could anybody tell me how many carbons are in this ring? And it's not a trick question. That's right. Just like Spinal Tap, right? It goes to 11, right? There's 11 carbons in this ring, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So look, when you want to draw the product, all you have to do is this. Your pen touches the paper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There you go. Put a carboxyl group on this end, put a carboxyl group on that end, and there you have it, my friends. There is your product, which is a diacid. Okay, this is actually called undecane. Undecane, what would it be? Dioic acid is what it would be called. Undecane dioic acid. You don't have to know that. We don't do carboxylic acid nomenclature until organic chemistry 2, and trust me, that's a beast on its own. All right, well that covers a bunch of new reagents. Now the last section on synthesis, before we get into just reviewing and practicing our synthesis strategies, is section 9.10. Okay, this is, I don't know how to say it. I don't want to say it's the most important, because that's not true. All reactions in organic chemistry have their place. However, what makes this section so special is this. It's really kind of your first, your introduction to increasing, not decreasing, but increasing the number of carbons in a carbon skeleton. I know that we've looked at it before in some regards, but this is where we really get into it, right? And what do you want to do in organic synthesis? Let's say you're trying to develop a new drug. You're always going to start with a molecule that's simple and then build one that's more complex. And that's what we really start doing in section 9.10. How do we do that? Well, we take advantage of the fact that a terminal alkyne can be deprotonated using amide as a base. We went all over that in the beginning of this chapter, last lecture, and we said we can make an alkynide. Okay, we can make an alkynide. We also said, okay, well, you could do the same thing with acetylene, right? And you could make this, which would be called an This would be called an acetylide, and we're going to see alkanides and acetylides. Well, here's where it gets interesting, because alkanides or an acetylide, they are good nucleophiles, right? You have a negative charge on a carbon, heck yeah, that's going to be a good nucleophile. And so they can do an SN2 reaction with an alkyl halide or any kind of alkyl that has a good leaving group attached to it. And look what you form, a new carbon-carbon bond. Now, I know that probably somebody who's hearing the sound of my voice is always wondering, how can I win the next Nobel Prize? You know, I'm really interested in going over to Europe and, you know, getting a big ceremony where they hand me a Nobel Prize. Well, I can tell you that the easiest way to get a Nobel Prize in organic chemistry, in my opinion, and I'm not alone, would be to develop a reaction where you make new carbon-carbon bonds. Okay, many organic chemists have won the Nobel Prize just for developing new methods for making carbon-carbon bonds, because it's not easy. Okay, I know we see carbon-carbon bonds everywhere in organic chemistry, but making them is actually not that trivial. So you've made a new carbon-carbon bond, and that is actually, as Joe Biden said to Barack Obama, this is a big deal. Okay, so what do we do? If we have a terminal alkyne, what can we do? We can treat it with a base like sodium amide. Now, what if we had an alkyl halide, like this is just ethyl iodide, right? Iodide is a very good leaving group. What's going to happen is when we form the intermediate alkanide, and I'm going to draw it here. So this would be the intermediate after the first step, right? What's that going to do? It's going to do an SN2, right? You're going to do a nucleophilic attack, loss of leaving group, and you formed a new carbon-carbon bond. So look, you started with a molecule that has 1, 2, 3, 4, 5. You got 5 carbons over here. Now you've got 1, 2, 3, 4, 5, 6, 7. You've grown the carbon skeleton from 5 carbons to 7 carbons. So that is really important. Now, I told you that you can also do the same thing with acetylene. I want you to focus in really carefully on this. It says acetylene can undergo 2 excessive alkylations. Why? Because it's got 2 protons with a pKa of 25. So if you treat it with sodium amide, followed by an alkyl halide, you can add a first R group. Now you can take your terminal alkyne and you do it again. Okay? What I want you to understand here is that with these 2 successive alkylations, order is not important. Okay, now I don't mean that you can just throw in sodium amide later or whatever, but I mean the order in which this is added and this is added. You could add either of them first. It doesn't matter. Okay, and we'll look at an example of that today. But now you've made 2 new carbon-carbon bonds. Holy moly, I could really go for 2 Nobel Prizes. Okay, there's got to be some perks that come with that. A new car or at least a Happy Meal gift certificate. Okay, anyhow, so we take our acetylene, treat it with sodium amide. Let's say we used ethyl iodide. We add a methyl group. And then we treat it with methyl iodide. We add a methyl group like that. Well, this is a stepwise procedure. And you know what? The way the book describes it, as I love his language sometimes, he said, although this might seem burdensome, okay, it said it might seem burdensome. Do I have to really set up 4 reactions? You know, first reaction, second reaction, third reaction, 4 reaction. It might seem like it's burdensome, but if you can end up with 2 new carbon-carbon bonds, you know, done, added, you know, selectively, I'd say it's pretty darn useful chemistry. All right. So there we go. So if we were starting with acetylene, let's say you just had some acetylene kicking around the lab. You know, they had a sale on acetylene over at, I don't know, Kmart. You know, where do they sell acetylene? Probably from a chemical supplier. But anyhow, let's say we had some acetylene and we wanted to make 1-butyne. Okay, we want to make 1-butyne. So let's draw the structure of acetylene. That is our starting material. And somehow we want to make 1-butyne. You guys know what 1-butyne is? It's a 4-carbon alkyne where the triple bond is on the first carbon, right? 1, 2, 3, 4, 1-butyne. Anyhow, what are we going to do? Well, the first thing we would do is we're going to deprotonate, right? We're going to remove one of the protons off of acetylene, right? Using sodium amide. Okay, what would that give us? Now I'm going to actually make it a little different here. Let me do this, and I will delete all of that. There we go. And I'm going to draw the intermediate because I can. Okay, so what's that going to do? The sodium amide is going to do a deprotonation like this, okay, you end up with this molecule, which is acetylide. Okay, what are you going to treat it with in the second step? Could anybody tell me what I would treat it with in the second step? And it's not a trick. Mr. Dion's not into trick questions. What would my electrophile be? All right, the acetylide is a nucleophile. It's seeking a nucleus. What would my electrophile be? Could anybody name it or describe it? How many carbons should there be in my electrophile? Yeah, thanks, Brooke. It's ethyl iodide, right? We need ethyl iodide. So there should be 2 carbons. So I have my iodine, 1, 2 carbons. Because then my acetylide could do the SN2 reaction, right? This is an SN2, right? This is my electrophile. I don't mean to sound like a jerk, but we didn't learn those terms for nothing, right? Nucleophile, electrophile, those are important terms. So first step, we treat it with sodium amide. Second step, we treat it with ethyl iodide. Do you have to know how to draw these arrows? You bet your bobby socks you do. Okay, you have to know how to draw the deprotonation. You've got to know how to draw an SN2 reaction mechanism. Okay, so let's make this next compound here. Now remember, the order of addition is not important, right? Because on this side we have an ethyl group, and on this side we have what's called a benzyl group. Okay, the ethyl group is going to be added through ethyl iodide, and the benzyl group is going to be added via benzyl iodide. Now, if you're wondering, Mr. Dion, why are you always picking iodide? You know, well, iodide is a better leaving group than bromide, which is a better leaving group than chloride. Here's the skinny on iodide, bromide, and chloride. Iodide is the most expensive. If you go to a chemical supplier and you buy an alkyl iodide, they cost a lot of money. If you're doing the reaction on small scale, though, they're very effective because, hey, who doesn't mind breaking the bank on a small scale reaction? You get a good yield, you go home happy, okay? Bromide's a little less expensive, but are not going to give you as high yield as an iodide. Chlorides, when would you use a chloride? Well, you could use a chloride in your paper synthesis, no problem. Chlorides are a lot cheaper than bromides or iodides, way cheaper. Chlorides are almost always used in a large scale reaction. Okay, they basically fine tune the conditions to give you a high yielding reaction, and they use chloride to save money. Anyhow, enough about that. So in the first step, we're going to treat this with sodium amide, and we're going to add, we could either add benzyl iodide or we could add ethyl iodide. Doesn't matter. Let's add ethyl iodide. I'll use the abbreviation ET, and we would end up with this molecule like this. Then in the second step, we're going to treat it with, the first step of this part, we're going to treat it with sodium amide, and then we're going to treat it with, with benzyl iodide. Are you, hey, you need me to take it? I cannot take it. Sure. All right. Okay, and then in the second step, we're going to treat it with benzyl iodide, which we can write like this, like that, and then we end up with our product like that. So just to give you a heads up, benzyl group, right? You could abbreviate that as BNI. It's the same thing as benzyl iodide. Anyhow, that's neither here nor there right now. All right, give me a thumbs up if you follow me on that. If you're like, you know what? Alkylation of a terminal alkyne. Hello, very cool chemistry, indeed. One great thing about organic chemistry is that it only gets more and more interesting and cool as you move along. You know, the good feeling about organic chemistry is that, you know, you kind of get the feeling like, hey, I can control nature and make it do what I want. I can make whatever I want, right? Okay, I remember the first time I heard a professor say that in university. Somebody asked him, oh, Dr. Grosser, could you make this molecule? And he said, I can make any molecule. At least he had confidence. All right, so let's move on. Section 9.11 is just kind of tying everything that we learned in Chapter 9 and bringing some other chemistry into it, tying it all together. So what are things you got to know? You got to know how to employ hydrogenation conditions, right? Using Lindlar's catalyst to give you a cis alkene, using sodium metal reduction to give you a trans alkene, all the other hydrogenation reactions. What else? Halogenation. We looked at halogenation of an alkene before. If we do, we take our dihalide, like this is one of the first reactions that we looked at. What the heck is that? One of the first reactions that we looked at in chapter 9 was taking a dihalide, treating it with excess sodium amide followed by water to give you an alkyne. Right? This is an alkyne synthesis, so you can imagine that's a very important reaction in this chapter. What can you do with an alkyne? Again, you can reduce it. You can do a halogenation followed by excess sodium amide and water to regenerate an alkyne. So just kind of playing with the double bond and triple bond there. And these are all the reactions that we've covered in this chapter. So you need to be fully cognizant of all these reactions. I've already gone over which mechanisms that you need to know. So I'm not going to spoon feed that to you on this slide and tell you exactly because I went over it in class. And several of these mechanisms aren't even included in our book, right? You look at the mechanism of ozonolysis, doesn't say anything in our textbook about the mechanism of ozonolysis of an alkyne. So let's go through all the reactions quickly. First reaction, right? We have two number ones here, number one and the second number one. That is just taking a geminal or a vicinal dihalide, right? The first one, this is geminal, a geminal dihalide. This one is a vicinal dihalide, treating it with excess sodium amide and water to produce an alkyne. The second reaction, if we treat that with HX, we can do a hydrohalogenation, and we could do a successive hydrohalogenation with excess HX. If we only use one equivalent of HX, then we're only going to add one molecule of HX in a Markovnikov addition across the triple bond. These reactions we covered this morning. So Markovnikov addition of water to produce a methyl ketone from a terminal alkyne. We use mercuric sulfate with sulfuric acid and water. We talked about anti-Markovnikov addition across a terminal alkyne using a hindered borane like 9-BBN, and then peroxide and sodium hydroxide. In the second step, we talked about enols. We talked about tautomerization. Then we said if you take one equivalent of chlorine or bromine, you can make a dihalide or a dihaloalkene. If you use excess, then you get a tetra haloalkane. We talked about ozonolysis of a terminal alkyne and internal alkyne. What else? And then the last section, we talked about alkylation, right? Deprotonation using sodium amide and then treatment with an electrophile. And then we can take that alkyne, we can reduce it to make a cis alkene using Lindlar's catalyst and hydrogen. We can reduce it to make a transalkene using sodium metal reduction, and we can just blow the smithereens out of it with hydrogen and palladium, platinum, or nickel to make an alkene. And those are the reactions those are the people in your neighborhood, right? Those are the reactions that we've looked at in this chapter. Well, in the interest of space, since I don't think I have enough space to really dissect each one of these problems on here, let me move to a blank sheet. What do I have? 9.29. What time is it? 8:53. We've got 3 more hours. So let me see here. No space there. Is there any room in here? Oh, yeah. There we go. So why don't we use this, and we're going to take a look at that question. So this is question 9.29 from our textbook. We'll start with A. We're starting with 1-butene, and we want to make that alkene. So that's what our first synthesis problem of the day is, okay? We want to do this transformation, and we have to come up with a set of reagents to affect this transformation. Well, I'm going to walk you through the first one, kind of get you started, get the ball rolling, if you will. The first thing I notice is that this molecule has 4 carbons. This second molecule is 1, 2, 3, 4, 5, 6 carbons. And so we have to increase the number of carbons in the carbon skeleton. What does that tell me? That tells me that at some point I've got to make a terminal alkyne, because the only way that we've learned to go from less to more carbons is to take a terminal alkyne and to do an alkylation, right? So how would I make a terminal alkyne, right? What I'm thinking is this: if I had $1 million, I'd be rich, right? If I had this terminal alkyne, okay, I could simply deprotonate that. I could treat it with ethyl iodide. Then I could reduce it using Lindlar's catalyst to give me the cis alkene, right? I could do that. Okay, well, how would I get from here to here then? How do I go from an alkene to an alkyne? Well, we really only have one way that we know that we could do that. The first thing we would do would be to treat it with bromine, Br2. Now, if you want to include a solvent, you can. Usually these kind of reactions are done in a chlorinated solvent like carbon tetrachloride. That is optional. You do not have to include that. I'll leave it out there for now. So if we were to do that, we'd end up with vicinal dibromide, right? We'd have a bromine here and a bromine here. Now this, again, is one of the first reactions that we looked at in this chapter. If we were to take this and treat it with excess sodium amide, we do that double elimination followed by a deprotonation. Then we put water in the reaction mixture, and we would end up with 1-butyne, like that. Now we have that acidic proton with that pKa of 25. If we treat that with sodium amide, okay, we don't need excess. And then in the second step, we treat it with ethyl iodide. We would end up with this compound. 1, 2, we'd have an ethyl group over here, and now we would have an ethyl group over here. So if I want to take an alkyne and reduce it to a cis alkene, what am I going to do? I'm going to use hydrogen in Lindlar's catalyst. And if you want to write poison catalyst, that's fine too. But that is how we do this kind of transformation. So if you're wondering, do I have to know how to do this? Absolutely. In fact, the remainder of organic chemistry until December will be mostly have to devise a synthesis. So how many steps do we have here? We have bromination, treatment with excess sodium amide, treatment with water, treatment with sodium amide again, alkylation, and reduction. So that's 1, 2, 3, 4, 5, 6 steps. It took us 6 steps to go from this alkene to the second alkene. So 6 steps. So you can see that you've got to know your reactions kind of frontwards and backwards, if you will, in order to become proficient in synthesis. Let's take a look at 9.29b. So B, we start with 1-butene, and we want to make, this is called butyraldehyde. Butyraldehyde, so that's propanol. There we go, butyraldehyde. Okay, well, a lot of these problems in Chapter 9, since we haven't learned that many reactions in organic chemistry, a lot of these problems can kind of be solved by process of elimination. How many ways have you learned how to make an aldehyde in this class? The answer is 1, right? The only thing that you've got under your hat is if you were to have 1-butyne, right, and you treated it with a hindered borane followed by H2O2, and sodium hydroxide. That's the only thing you've got under your hat to do that transformation. Have a terminal alkyne and do an anti-Markovnikov addition of water to get that enol that tautomerizes to give you an aldehyde. That's the only thing you have. By the time you get to end of organic chemistry 2, trust me, you'll have a whole toolbox of different reactions to make aldehydes, but right now you've only got 1. So let's work with that. How are we going to go from this alkene to this alkyne? We're going to use the exact same strategy we did in the last problem. First, we're going to treat it with bromine. This time I'm going to add a solvent, carbon tetrachloride. It is a carcinogenic solvent, CCl4. Having said that, back in the 70s, chemists used to wash their hands with it. Okay, so you know, things were different then, right? Anyhow, so we're going to add a bromine here and a bromine here. Then what are we going to do? We're going to make that terminal alkyne. First by treatment with excess sodium amide to do the double E2, followed by treatment with water, and that is going to give us the terminal alkyne, 1-butyne. Then what do? We're going to treat it with our hindered borane. Let's try 9B. Now, let me keep it the same. I don't want to ruin your life here. Let's do R2BH. And then the second step, we're going to treat it with peroxides and sodium hydroxide. Like that. There you have it, my friends. What do you think? Give me a thumbs up if you think you could do that one. That one is only 5 steps. And I'm sure there's somebody who's thinking, you know, how many steps are we going to get up to? How many steps? Well, I'd say at the end of organic chemistry 2, probably 8 or 9 steps is probably the most steps that we'll ever look at in a problem. But again, don't be intimidated by this kind of problem because you're going to see a lot of them over the course of organic chemistry. And I promise you that if you practice them, and I don't like to promise things to people, but I promise that if you practice them, that you will become proficient, and you're really going to get those reactions memorized. You will really start to memorize those reactions. Well, I'm going to skip C for now, And I'm going to move on to 9.29D. What time is it? I'm going to move on to 9.29D. Again, the answer to C is in the solutions manual. I want to move on. This is 9.29D. So we're starting with we're starting with 1-butene again. The author is kind of obsessed with 1-butene, and we want to make 1-butanol. So we want to make this primary alcohol. Anyhow, so we want to make this alcohol. Does anybody have an idea that they could express over Microsoft Teams about where we might start on this kind of thing? I'll take any suggestion while you're thinking. I'm going to turn on my heater. Since it's so cool today. Does anybody have a suggestion? No? Okay. Well, if we don't have a suggestion, let's think about retrosynthesis. If I want to make a terminal alcohol, okay, I really only have one option to me based off of what I've learned in this class. The only thing that you could do to make that alcohol would be to start with this terminal alkene and treat it with borane, THF, and then peroxides and sodium hydroxide. That's the only option that you've got to do an anti-Markovnikov addition of water across a double bond. Okay? We're not going to use mercuric sulfate because that would give us a methyl ketone, right? If you were to take this and treat it with, sulfuric acid, mercuric sulfate, water, you would end up making this compound, 2-butanone, right? You'd end up with a methyl ketone. So that's not going to work, right? So what I'm trying to get at with you guys is, if you're ever stuck, you can just ask yourself, well, how many ways do I know to make an alcohol like this? The only thing that you've ever learned in this class to make an alcohol on the end of a molecule like that is to do an anti-Markovnikov addition across a double bond. And so the question then becomes, how do I get from the triple bond to the double bond? All I have to do is a reduction. I can reduce it with hydrogen and Lindlar's catalyst, and that will give me 1-butene. And I know what you're thinking, like, couldn't you use sodium metal and liquid ammonia? And the answer is yes. So we'll put sodium and liquid ammonia. That will work. If you look at our textbook in the solutions manual, he's almost always going to choose to do Lindlar's catalyst. The reason why is because anytime that we can avoid using sodium metal, we will. So then all we have to do is take this, and we're going to treat it with borane and THF, and then in the second step with peroxides and sodium hydroxide, like that. A student asked, why can't I just use bromine? So if I start with this, why can't I just treat it with bromine? So I'm not sure how that would help us, because if we only used one equivalent of bromine, we would end up with this kind of molecule. Okay, if we only had one equivalent of bromine, but that doesn't get us any closer to anything that's useful. And if we were to treat it with excess bromine, then we'd have 2 bromines here and 2 bromines here. And that doesn't get us anywhere either. Okay, that's not going to help us get to our product. Does that help? Okay. All right, let's move on to E. So this is 9.29E. We've got 1-butene again. The author is obsessed with 1-butene, and we want to make this compound. Let me make sure I'm writing this down properly. What am I looking at? E? Yeah, I'm writing it down differently than they have it in the book. So let me make sure I have it written down the exact same way. So we want to make this compound. Okay, where we have a bromine going up and a bromine going down. There's a couple of ways to do this synthesis. And this is kind of your introduction into the whole concept of there's more than one way to do a reaction in organic chemistry. Because you might notice that this is a meso compound, isn't it? Right? If we rotate that carbon-carbon bond 180 degrees, we end up with this compound, okay, like this, which is, this is a meso compound, okay? Remember, we went over this quite a bit in the alkenes chapter. This, it doesn't look like a meso compound there, but it is a meso compound when you look at this conformation. So what would we do? How would we make a meso compound? Well, the thing is, I have no way of adding two bromines across an alkene in a syn fashion, but I do know how to add two bromines across an alkene in an anti fashion. So that tells me that retrosynthetically, if I had this trans alkene like this, all I'd have to do is to treat it with bromine, and I would get anti-addition, and I'd end up with one bromine up and one bromine down. So then the question becomes, how do I go from here to here? Well, the first molecule, my starting material, has 4 carbons, and my product has 6 carbons. The only way that we know how to increase the size of the carbon skeleton would be to first treat it with sodium amide, and then in the second step to treat it with ethyl iodide. That would give us this compound. Okay, we've got this compound here. Now we want to reduce that to a trans alkene. How do we do that? We have to use sodium metal reduction. So we use sodium in liquid ammonia. We end up with the trans, oops, that's not very pretty, is it? We end up with the trans alkene. And then we do the anti-addition of bromine. So this is, remember, bromination is anti-addition across the double bond, and we end up with one bromine up and one bromine down, and that is our product, which happens to be a meso compound. Anyhow, there we go. Well, we got time for one more, I think, and this one is in a similar vein to that problem, 9.29F. So 9.29F. Now we're going to take the one butene molecule, and we want to make this compound, which is not a meso compound, or I have one bromine going down and one bromine coming up. So if you compare the two answers, right, this one, both of them were up, and now I want to make this compound where one is up and one is down. And so that tells me that I have to do a bromination of, right, I'd have to do an anti-bromination on the cis alkene, right? I'd have to start with the cis alkene for the bromination. And since it is anti-addition, I end up with one bromine up and one bromine down. So how am I going to go from here to the cis alkene? Well, here I've got 4 carbons. Here I've got 6 carbons. So what are we going to do first? We're going to treat it with sodium amide as our base, ethyl iodide in the second step. That's going to produce this alkene, or sorry, this alkyne rather. Then we want to reduce that to a cis alkene. So we're going to treat it with hydrogen and Lindlar's catalyst, like that. And then we would end up with this cis alkene, like this, right? It's cis because both hydrogens are on the same face of the molecule. And then we treat that with bromine, like that. So we have a total of 4 steps. 4 steps for this reaction. If you go back to 9.29E, it was also 1, 2, 3, 4. It was also 4 steps. Okay, and I can just put this bug in your ear that in our textbook, he asks lots of questions about, you know, having to understand, you know, when one bromine is up and one bromine is down, you know, when both bromines are on the same face of the molecule. Same thing with hydroxyls, because we look at both syn and anti-dihydroxylation. So all that stuff is important. All right. Anyhow, there we go. So let's try another problem. So I have some more problems. I want to try, let's try this one. This one might be actually a step a little easier. This is question, okay, And try not to look at the solutions manual. The solutions manual will not help you if you haven't learned the reactions. It will not help you. It will only be deleterious to your learning. It's very easy to look at a solutions manual and say, oh, yeah, I get it. But when you're alone in the examination room and Respondus is running, you can't just say, oh, yeah. You have to know it. It's got to be in your brain. So that's not me trying to sound like a jerk. It's just the reality. All right, so if I start with this geminal dibromide, right? If the two bromines are on the same carbon, this is geminal. So it's a geminal dibromide. So this is just a descriptor. How am I going to convert it into this terminal alkene? Well, I know that if I treat this with excess sodium amide, and in the second step, I treat it with water, I'm going to end up with this alkyne, 1-butyne. Then I can just simply reduce this using hydrogen and Lindlar's catalyst to give me an alkene. Now remember, if it's a terminal alkene, it's not cis or trans, right? This isn't cis or trans because both of these hydrogens are identical, right? One of them is cis to this hydrogen, the other one is trans to it. So there's no cis or trans here. So you could use that, or you could use sodium metal reduction. One last thing I want to point out to you, and it's going to take me a second here because I don't have my textbook open, but there is a problem in the textbook, and I don't mean like a problem like an issue with text. I mean a problem that you have to practice. This is the last thing I'll say, and just give me a second here to find it. It'll just take me to Shakes of a Lamb's Tail. Preparation of alkynes. It's question 9.8. Okay, I want everybody to take a look at question 9.8. Okay, before stepping into the quiz room, because a good question to ask here would be this. Well, I've got beta protons here, Mr. Dion, to do my elimination to make the triple bond here, but I also have beta protons here. Why couldn't I pull these ones off and end up making this alkyne? That would be a really good question, okay? And the answer is in question 9.8. It gives you an example where you do a double elimination on a geminal dihalide where the halogens are inside the molecule, meaning this. You start out with 1, 2, 3, 4, 5. You end up with both halogens here. And when you treat this with excess sodium amide, instead of making the triple bond inside, what it does is it ends up isomerizing, and you end up with this compound. So 1, 2, 3, 4, 5. You end up with this alkynide in the end. Okay, it's going to undergo isomerization. This is something that I think I might include in my slides for the next time I teach the class. But a student asked me a question at this one time, and I said, that's a very good question, and it is addressed in question 9.8. So be sure to take a look at that question before you step into the quiz room.